Integration of linear-over-square-root-of-quadratic functions. Welcome back. In this section, we're going to tackle a specific type of integration problem. We'll be learning how to evaluate integrals where the top part, the numerator, is a linear polynomial, meaning it's something like px plus q, and the bottom part, the denominator, is the square root of a quadratic polynomial. Now let's look at the general form of these integrals. You'll see it written as integral with the indefinite integral symbol of px plus q divided by the square root of x squared plus bx plus c with respect to x or dx at the end. The main difficulty with these integrals is that the numerator, px plus q, isn't simply the derivative of the expression inside the square root, x squared plus bx plus c. If it were, the integration would be much easier. So, to overcome this, we'll use a clever technique. We're going to split this single integral into two separate, more manageable integrals. One of these will be solvable using a straightforward substitution method. You'll recall those from earlier work, and the other will rely on some standard formulas we've learned for integrating irrational functions, specifically those involving square roots. In the following slides, we'll break down exactly how to do this splitting and solve each part. Keep in mind, mastering this technique will be very useful when you encounter more complex integration problems later on. 1. The core strategy. Okay, so let's move on to slide 2, where we really get into the core strategy for tackling these integrals. As we discussed on the previous slide, the main difficulty arises because the numerator, px plus q, isn't a straightforward derivative of the expression inside the square root. Therefore, our goal here is to cleverly rewrite that linear numerator, px plus q, as a combination of two things, the derivative of our quadratic expression, x squared plus bx plus c, and a simple constant. Think of it like breaking down a complex term into more manageable pieces. Let's define our quadratic expression as f of x equals x squared plus bx plus c. This is just to make things a little cleaner to work with. Now, if we take the derivative of f of x, we get f prime of x, which is equal to 2x plus b. Remember your basic differentiation rules, the power rule applied to each term. Now here's the key step. We want to express px plus q in the following form. Px plus q equals a times 2x plus b. A and b are constants, meaning they're just numbers that we need to figure out. What we're doing is essentially saying, can we find values for a and b that allow us to rewrite px plus q using the derivative of our quadratic and a constant? If we can, it unlocks the solution. Once we successfully rewrite the numerator in this way, the original integral beautifully splits into two separate integrals. Let me write that out. The integral from px plus q over the square root of x squared plus bx plus c dx becomes a times the integral of 2x plus b over the square root of x squared plus bx plus c dx plus b times the integral of 1 over the square root of x squared plus bx plus c dx. Notice how this separation is crucial. The first integral, with 2x plus b in the numerator, will be solvable using a simple substitution, as we'll see on slide 3. The second integral, with just a constant 1 in the numerator, is a standard irrational integral that we've likely encountered before. So, by strategically rewriting the numerator, we've transformed a tricky integral into two much more manageable ones. This is the heart of the method, and we'll build on this in the following slides by actually finding those constants, a and b, and solving the resulting integrals. 2. Step-by-step breakdown of the method. Okay, so let's move on to slide 3. This slide outlines the step-by-step method for tackling these integrals where we have a linear expression over the square root of a quadratic, as we discussed in the previous slides. Remember, the core idea is to cleverly rewrite the integral to make it solvable. Here, we're going to break down exactly how to do that. It's a systematic approach, so if you follow these steps, you'll be able to handle a wide variety of these problems. Step 1. Identify the quadratic expression. This is pretty straightforward. We need to pinpoint the quadratic expression that's sitting inside the square root in the denominator. We're calling it f of x, and it's defined as a x squared plus bx plus c. Just pull that out and clearly identify what a b and c are in your specific problem. Step 2, find the derivative. Once you've identified the quadratic, the next step is to find its derivative. Remember your basic calculus. The derivative of ax squared plus bx plus c is 2ax plus b. We're denoting this derivative as f prime of x. This derivative is crucial because we're going to use it to rewrite our numerator. Step 3, determine constants a and b. This is where the algebraic manipulation comes in. We want to express the original numerator, which is px plus q, as a combination of our derivative, 2ax plus b, and a constant. So we're saying that px plus q can be written as a times 2ax plus b, where a and b are constants that we need to figure out. To find a and b, we compare the coefficients of x and the constant terms on both sides of the equation. Think of it like this. The coefficient of x on the left side is p, and on the right side it's 2a. So p must equal 2a, allowing you to solve for a. Then the constant term on the left is q, and on the right it's b. So q equals b. Step 4, split the integral. Now that we've rewritten the numerator, we can split the original integral into two separate integrals. This is the key step that makes the problem manageable. The first integral, which we're calling I sub 1, is a times the integral of 2ax plus b divided by the square root of ax squared plus bx plus c. The second integral, I sub 2, is b times the integral of 1 divided by the square root of ax squared plus bx plus c. Step 5, solve the first integral I sub 1. This first integral is designed to be a simple u substitution problem. We let u equal our quadratic expression, ax squared plus bx plus c. Then, du is simply the derivative of that, which we already found, 2ax plus b. So the integral becomes the integral of du over the square root of u, which simplifies to 2 times the square root of u plus a constant of integration. Substituting back for u, we get I sub 1 equals 2a times the square root of ax squared plus bx plus c. Step 6, solve the second integral, I sub 2. The second integral is a standard irrational integral. It often requires a technique called completing the square. We manipulate the quadratic expression, ax squared plus bx plus c, to rewrite it in a form where we have a perfect square plus a constant. Once we've completed the square, we can use standard integral formulas, like the integral of 1 over the square root of x squared plus a squared, or a squared minus x squared, to solve for I sub 2. So that's the complete method. It might seem like a lot of steps, but each one is relatively straightforward. We'll see it in action on the next slide with a worked example, and then we'll discuss some common mistakes to avoid. Remember, the goal is to transform the integral into something we know how to solve. 3 worked example. We're given the integral of 2x plus 3 divided by the square root of x squared plus 4x plus 8 with respect to x. Step 1, identify the quadratic and its derivative. First, we need to identify our quadratic expression. Looking at the denominator, we can see that f of x is equal to x squared plus 4x plus 8. Remember, this is our f(x) that we've been talking about in the previous slides. Next, we find the derivative of this quadratic. So f prime of x, which is the derivative of f(x), is equal to 2x plus 4. Don't forget your power rule and the constant multiple rule when differentiating. Step 2, express the numerator in terms of the derivative now, the key step. We want to rewrite our numerator, 2x plus 3, in terms of the derivative we just found, 2x plus 4, and a constant. We're essentially saying that 2x plus 3 can be written as a times 2x plus 4 plus b, where a and b are constants we need to determine. Let's write that out. 2x plus 3 equals a times 2x plus 4 plus b. To find a and b, we compare coefficients. Looking at the x terms, we have 2x on the left side and 2ax on the right side. Therefore, 2 equals 2a, which means it equals 1. Now, let's look at the constant terms. On the left side, we have 3. On the right side, we have 4a plus b. Since we know a is 1, we have 3 equals 4 times 1 plus b. Solving for b, we get b equals -1. Step 3, split the integral. Great. Now that we've rewritten the numerator, we can split our original integral into 2 separate integrals. This is where the strategy from slide 2 really pays off. we have the integral of 2x plus 3 divided by the square root of x squared plus 4x plus 8 dx, which becomes the integral of 2x plus 4 divided by the square root of x squared plus 4x plus 8 dx, minus the integral of 1 divided by the square root of x squared plus 4x plus 8 dx. Step 4. Solve the first part, I sub 1. Let's tackle the first integral, which we'll call I sub 1. Notice that the numerator, 2x plus 4, is exactly the derivative of the expression inside the square root, f prime of x. This is fantastic. This means I sub 1 is equal to 2 times the square root of x squared plus 4x plus 8. Remember from slide 3, the integral of f prime of x over the square root of f of x is simply 2 times the square root of f of x. Step 5. Solve the second part, I sub 2. Now for the second integral, I sub 2. This one requires a bit more work. We have the integral of 1 divided by the square root of x squared plus 4x plus 8 dx. To solve this, we need to complete the square. Completing the square for x squared plus 4x plus 8, we get x plus 2 squared plus 4. So, I sub 2 becomes the integral of 1 divided by the square root of x plus 2 squared plus 4 dx. This now fits a standard integral form. Recall the formula. The integral of 1 divided by the square root of x squared plus a squared is equal to the natural logarithm of the absolute value of x plus the square root of x squared plus a squared. In our case, a squared is 4, so it is 2. Applying the formula, we get the natural logarithm of the absolute value of x plus 2 plus the square root of x plus 2 squared plus 4, which simplifies to the natural logarithm of the absolute value of x plus 2 plus the square root of x squared plus 4x plus 8. Final answer. Finally, we combine both parts, I sub 1 and I sub 2, and don't forget the constant of integration. See therefore, the integral of 2x plus 3 divided by the square root of x squared plus 4x plus 8 dx is equal to 2 times the square root of x squared plus 4x plus 8, minus the natural logarithm of the absolute value of x plus 2 plus the square root of x squared plus 4x plus 8, plus c. Okay, let's tackle a worked example to solidify our understanding of integrating linear expressions over the square root of a quadratic. This will really bring everything we've discussed into focus. And there you have it. We've successfully evaluated this integral using the method we've been building up over the last few slides. Remember to review the common mistakes on the next slide to avoid those pitfalls. 4. Real-world application context. So, this slide highlights the practical applications. While these integrals, with a linear term over the square root of a quadratic, might seem abstract at first, they actually pop up quite frequently in fields like physics and engineering. Specifically, the slide gives 2 examples. The first is calculating the escape velocity of a rocket. Escape velocity is the speed a rocket needs to achieve to break free from a planet's gravitational pull. The formula for escape velocity involves distance, and when you're working with gravitational forces and distances, you often end up with integrals of this exact form, a linear term divided by the square root of a quadratic expression involving distance. The second example is determining the electric potential of a point charge relative to a distance. In electromagnetism, electric potential describes the amount of work needed to move a charge from one point to another. Again, this calculation involves distance, and the relationship between the variable, which is distance in this case, and the rate of change often leads to integrals that look just like the ones we've been practicing. Essentially, whenever you have a quantity that changes with distance, and you're dealing with rates of change, these types of integrals are likely to appear. Okay, let's move on to slide 5. Now that we've mastered the how of solving these integrals, splitting them, finding the constants, and applying the appropriate techniques, it's important to understand why we learn this. It's easy to get lost in the mechanics and wonder when you'd actually use this in a real-world scenario. Now, keep in mind that we won't necessarily be solving these physics or engineering problems from scratch in this course. But understanding that these mathematical tools are used to model real-world phenomena helps solidify the concepts and shows you the power of integration. And as we move on to slide 6, we'll look at some common pitfalls to avoid, so you can confidently tackle these problems. 5 common mistakes to avoid. Okay, let's move on to slide 6. This slide is really important because it highlights the most common pitfalls students encounter when tackling these types of integration problems. We've learned the strategy, we've seen a worked example, and now we need to make sure you avoid making these frequent mistakes. First, let's talk about incorrect derivatives. A surprisingly common error is messing up the derivative. Remember, when we have a quadratic expression in the form of a x squared plus bx plus c, its derivative isn't just a x. It's 2x plus b. Don't forget to multiply the coefficient of the x squared term by 2 before taking the derivative. This is crucial because the whole method relies on correctly identifying the derivative to split the integral. Next, we have sign errors in b now. Recall how we rewrite the numerator, px plus q, as a times the derivative of our quadratic plus b. So, we have px plus q equals a times 2x plus b plus b. When you're solving for b, it's easy to make a mistake with the arithmetic, especially if it isn't equal to 1. Be very careful when subtracting to isolate b. Don't just subtract the constant term from q without considering how a is multiplied with b. Take your time and double-check your calculations here. Moving on, we have forgetting the constant of integration. This is a classic mistake in all integration problems, not just this type. Remember, whenever you find an indefinite integral, you always need to add the constant of integration, which we denote as plus c. It represents the family of all possible antiderivatives. Leaving it out will result in a technically incorrect answer, even if the derivative of your answer matches the integrand. Finally, let's discuss completing the square errors. As you saw in the worked example, we often need to complete the square to solve the second integral, the one involving just 1 over the square root of the quadratic. When completing the square, it's easy to make mistakes with the constant term you add and subtract. Make sure you're applying the completing the square process correctly and that you're handling that constant term accurately inside the square root. So, keep these 4 points in mind as you practice. Avoiding these common errors will significantly improve your success rate with these integrals. Now, let's move on to the final slide where we'll summarize the key takeaways. 6 key takeaways. Okay, let's recap everything we've learned about integrating functions of the form linear over the square root of a quadratic. This slide, slide number 7, summarizes the key takeaways, the essential things you need to remember to successfully tackle these types of integrals. First point, the goal: split the integral into a derivative part and a constant part. Remember, the core challenge with these integrals is that the numerator isn't quite the derivative of what's under the square root. So, our strategy, as we discussed, is to cleverly rewrite the numerator so we can create a part that involves the derivative and another part that's just a constant. This splitting is the key to making the integration manageable. Next, the formula, px plus q equals a times the quantity 2x plus b. This is the workhorse equation. This is how we express the linear numerator, that's px plus q, in terms of the derivative of the quadratic, which is 2x plus b, and a constant, b. Finding the values of a and b is a crucial step, as we saw in the worked example. We do this by comparing coefficients on both sides of the equation. Moving on, the result of part 1, the integral of f prime of x over the square root of f of x equals 2 times the square root of f of x. This is a fantastic result. Once you've successfully split the integral and identified the derivative part, this is what that part simplifies to. Remember, f prime of x represents the derivative of the quadratic function f of x, which is a x squared plus bx plus c. And the integral of that derivative, divided by the square root of the original quadratic, is simply 2 times the square root of the quadratic. This is a direct application of u substitution, as we discussed. Finally, the result of part 2 requires completing the square and applying standard irrational integral formulae. The constant part of the integral, after the split, isn't quite as straightforward. It usually involves completing the square within the square root to get it into a standard form. Then, you'll need to recall and apply one of the standard integral formulas for irrational functions, things like the integral of 1 over the square root of x squared plus a squared, or 1 over the square root of a squared minus x squared. We covered those in previous sections, so make sure you're comfortable with those formulas. So, to reiterate, mastering these 4 points will give you a solid foundation for solving these integrals. Remember the goal, the formula for splitting the numerator, the result of the derivative part, and how to handle the constant part. And don't forget to look out for those common mistakes we discussed on the previous slide.